From the vast cosmic dark, one world shines with an unmistakable vibrancy. A swirling marble of blue, green, and white, cradled perfectly in the Goldilocks zone. For generations, we've called it home, the ultimate sanctuary, a peerless cradle of life. This is Earth, the planet we've always believed to be the absolute best. But what if our deepest assumptions about Earth are merely echoes of our own limited perspective? What if our cherished home, with all its stunning beauty and biological complexity, isn't quite the cosmic pinnacle we imagine? What if best is a far more complex equation? We often define the ideal world by our own existence. A planet with liquid water, a breathable atmosphere, stable temperatures conditions mirroring our own. Yet the universe operates on scales and principles far beyond our immediate understanding, teeming with possibilities we're only beginning to glimpse. For all its apparent perfection, Earth is a world born of cataclysm, constantly shaped by powerful destructive forces. Its surface is scarred by ancient impacts, its climate prone to dramatic shifts, its geological engines ceaselessly reshaping its very foundations. We often overlook the relentless churn beneath our feet. Volcanoes erupt, continents drift, and oceans rise and fall across immense geological timescales. This isn't a static paradise. It's a dynamic, often violent cosmic engine that has, by sheer chance, fostered life. Our human lifespan, a mere blink in cosmic time, gives us a false sense of stability. Yet Earth's history is a turbulent saga of ice ages, mass extinctions, and atmospheric transformations. It has been a survivor, not always a comfortable home. Imagine worlds bathed in the light of binary suns, planets orbiting ancient red dwarfs, or even rogue worlds drifting through interstellar space, warmed by internal geological heat. The cosmos presents an endless canvas of planetary forms. Our Goldilocks zone concept, while useful, is inherently Earth-centric. What if life, in its myriad forms, thrives in conditions we currently deem hostile? What if the truly best world for life looks nothing like our own? Could there be planets with atmospheric compositions far more protective, geological activity more nurturing, or magnetic fields more robust, shielding against stellar radiation with unparalleled efficiency? Perhaps true planetary advantages lie hidden. Even on Earth, life flourishes in the most extreme environments, boiling hydrothermal vents, deep polar ice, or arid deserts where water is a myth. These pockets of resilience whisper of life's adaptability far beyond our narrow comfort zones. This question forces us to reconsider everything we thought we knew. For centuries, our perception of a best planet has been inherently anthropocentric, centered solely on human needs and experiences. But to truly assess a world's potential, we must detach from our terrestrial bias and redefine what best truly means beyond just our comfort. Our bias is natural. Earth is our home, after all. We measure every other world against the lush forests, vast oceans, and breathable air we take for granted. Yet these very conditions, perfect for us, might be limiting factors in the grand cosmic scheme, preventing other, perhaps superior, forms of life from emerging. The most common metric is habitability. But is habitable merely a place where life could exist, or a place where life can thrive and diversify without constant existential threat? We often equate habitability with Earth-like conditions, overlooking the vast spectrum of environments life could conquer. A truly ideal world might offer more than just a surface temperature within the Goldilocks zone. It could possess a resilient atmosphere, a stable magnetic field, or unique geological activity that actively fosters life's emergence and evolution over billions of years, far more effectively than Earth. Then there's stability. Earth experiences ice ages, supervolcano eruptions, and asteroid impacts. While life persists, these events cause mass extinctions. Could there be a world with far greater geological and climatic stability, allowing life to evolve uninterrupted for even longer stretches of time? Imagine a planet where climatic shifts are minimal, where plate tectonics gently recycle crust without cataclysmic quakes, and where stellar radiation is perfectly constant. Such a world might offer an evolutionary playground far superior to our own, promoting biodiversity and complex ecosystems. Climate isn't just about temperature, but also about its long-term resilience. Earth's climate is a delicate balance, easily disrupted by both natural forces and, increasingly, by its dominant species. A truly best planet might have inherent mechanisms to buffer against extreme changes. Perhaps a world with a more massive ocean or a dynamic atmospheric composition could regulate its temperature and weather patterns with greater efficiency and fewer devastating extremes. The ideal climate isn't static, it's one that can adapt and recover gracefully. Protection extends beyond a strong magnetic field deflecting solar winds. It involves defenses against cosmic radiation, asteroid bombardment, and even the hazards of a chaotic planetary system. Earth has its moon, but is that sufficient, or could other configurations be better? Our planet benefits from Jupiter's gravitational shielding, largely clearing inter-system asteroids. Yet devastating impacts still occur. A truly protected world might orbit in a much emptier region of space, or possess a ring system that acts as a perpetual cosmic shield. We often picture Earth as a tranquil blue marble, a perfectly balanced ecosystem operating in harmony. This serene image, however, masks a turbulent reality. Our planet is a dynamic, restless world, constantly in flux, shaped by forces far beyond our control. Its stability is an illusion we cherish. Beneath the thin veneer of soil and ocean, colossal tectonic plates grind and collide, reshaping continents over eons. This relentless geological activity is the primary engine of Earth's instability, responsible for some of its most dramatic and destructive events. It's a constant, slow-motion ballet of destruction and creation. Earthquakes, violent tremors that rip through the crust, are stark reminders of this subterranean struggle. Cities can crumble in seconds, landscapes deform, and lives are irrevocably altered by these sudden releases of immense pressure. They demonstrate a fragility beneath our very feet. Volcanic eruptions further underscore this planetary volatility. From silent, oozing lava flows to explosive pyroclastic clouds, volcanoes are Earth's safety valves, releasing internal heat and pressure. Yet they can devastate vast regions, burying towns and altering global climates for years. The very air we breathe is a swirling, chaotic system. Our atmosphere, while vital for life, is also a powerful engine of destruction. It orchestrates massive storms, from towering hurricanes to devastating tornadoes, which unleash incredible energy upon the planet's surface. These atmospheric giants carve paths of destruction, tearing down infrastructure, causing widespread flooding and reshaping coastlines. The forces unleashed are a stark contrast to the calm skies we often take for granted, showing nature's raw, untamed power. Even the most fundamental elements, like water, become agents of chaos. Torrential rains lead to catastrophic floods, submerging communities and displacing millions. Rivers overflow their banks, turning once fertile plains into temporary destructive inland seas. Conversely, prolonged droughts turn lush landscapes into arid wastes. The absence of water can be just as destructive as its excess, leading to wildfires that scorch millions of acres, destroying habitats, and casting vast plumes of smoke into the atmosphere. Wildfires, often intensified by dry conditions, rage across continents annually. They leave behind charred remains, turning vibrant forests into desolate, blackened landscapes, contributing to air pollution and accelerating the cycle of planetary stress. Earth's climate has never been truly static. Throughout its long history, our planet has swung between ice ages, where glaciers covered vast continents, and periods of intense warmth, drastically altering sea levels and ecosystems. From its very birth, Earth was a crucible of fire and impact. Billions of years ago, a relentless bombardment of asteroids and comets sculpted its nascent surface, transforming a molten rock into a world scarred by unimaginable violence. This wasn't a gentle formation, but a brutal cosmic struggle, setting a precedent for the chaos that would repeatedly define its future. The Hadean Eon, aptly named after Hades, was a period of constant cosmic assault. Craters formed and reformed, erased by volcanic activity and a restless crust. This early trauma wasn't merely a phase. It forged the very foundations of our planet, infusing its geology with a memory of cataclysm. It's a violent origin story often overlooked. But these aren't just ancient echoes. Even as life began to tentatively emerge, the sky remained a threat. The impact that formed the moon, while beneficial in the long run for tidal forces, was an event of planet-shattering proportions. Later, smaller yet still devastating, impacts continued to reshape nascent ecosystems. Perhaps the most famous, and certainly the most impactful on complex life, was the Chicxulub asteroid. 66 million years ago, an object the size of a mountain struck the Earth, unleashing an energy equivalent to billions of atomic bombs. This single event didn't just kill dinosaurs, it reset the planetary clock for evolution. The immediate aftermath was a global winter. Soot and dust choked the atmosphere, blocking sunlight and plunging the world into darkness. Temperatures plummeted, plants withered, and the food chain collapsed. This was not an isolated incident, but a stark reminder of Earth's vulnerability to extraterrestrial forces. Yet impacts are only one chapter in Earth's catastrophic tale. Deep beneath the planet's surface, another force of immense destructive power constantly churns. Supervolcanoes, not just isolated peaks but vast volcanic provinces, have periodically erupted, unleashing devastation on an even grander scale. Consider the Siberian Traps, a flood basalt event that occurred about 250 million years ago. For millions of years, unimaginably vast quantities of lava poured from fissures, covering an area the size of Europe. The gases released acidified oceans and poisoned the atmosphere, triggering the Permian-Triassic extinction. This wasn't a quick catastrophe, but a prolonged planetary assault. The climate spiraled out of control, marine life suffocated, and terrestrial ecosystems crumbled. Up to 96% of all marine species and 70% of terrestrial vertebrate species vanished. It was Earth's most severe known extinction event. The Deccan Traps in India, active around the same time as the Chicxulub impact, also played a role in the end Cretaceous extinction. Their vast outpourings of magma further stressed an already fragile global environment, contributing to the demise of countless species. These geological titans demonstrate that Earth's internal processes can be just as, if not more, destructive than external threats. The very dynamism that drives plate tectonics, responsible for mountains and continents, also harbors the potential for unparalleled planetary devastation. We often picture Earth as a steadfast shield, cradling life within its gentle embrace. But this comforting image might be a dangerous illusion. The truth is, our planet is a battleground where life persists not because of absolute safety, but despite constant existential threats that relentlessly test its resilience hour after hour, day after day. Consider the invisible onslaught from space, radiation. High-energy particles from the sun and distant galaxies constantly bombard our world. While our atmosphere and magnetic field offer some defense, they are not impenetrable. These silent killers pose a continuous, underlying danger to every living cell, shaping evolution itself in subtle, often devastating ways. Solar flares, massive eruptions from the sun, unleash torrents of charged particles. When these coronal mass ejections strike Earth, they can overwhelm protective layers, leading to increased radiation exposure. For astronauts, it's an immediate hazard. For life on the surface, it's a cumulative burden, slowly eroding biological systems over generations, pushing adaptation to its limits. Beyond the sun, galactic cosmic rays, fragments of exploded stars, travel across vast cosmic distances with incredible energy. These particles penetrate deeper, capable of damaging DNA and increasing mutation rates. Earth's magnetic field deflects much of this, but enough still reaches the surface to remind us of our precarious position in a violent universe. Our planet's magnetic field, generated by the churning liquid iron core, is our primary defense against these cosmic bombardments. It wraps Earth in an invisible shield, diverting most harmful particles around us. Without this geomagnetic bubble, our atmosphere would be stripped away, and the surface would be bathed in sterilizing radiation, making complex life impossible. But this shield is not static or perfectly uniform. It fluctuates, weakens in places, and is subject to monumental shifts. Scientific data reveals areas where the magnetic field is currently thinning, creating vulnerabilities. The South Atlantic anomaly, for example, allows more radiation to penetrate closer to the surface, impacting satellites and potentially ground-level organisms. Even more dramatically, Earth's magnetic poles periodically reverse. This isn't a quick flip. It's a process that can take thousands of years, during which the field weakens significantly, becoming chaotic and fragmented. Such a period would expose our world to unprecedented levels of radiation, profoundly challenging all life, altering ecosystems irrevocably. Then there's the atmospheric erosion. Earth's atmosphere, vital for breathing and temperature regulation, is constantly under attack from the solar wind, a stream of charged particles emanating from the sun. Our magnetic field largely protects us, but over geological timescales, a measurable amount of gases are still lost to space, thinning our protective blanket. While the loss rate seems minor today, over billions of years, a planet could slowly bleed its life-giving air into the void. This raises a critical question for what constitutes an ideal world. Is a planet truly best if its fundamental protective layers are in a slow, continuous decline, demanding constant repair or adaptation from its inhabitants? Beyond external threats, Earth's internal systems also operate on razor-thin margins. We often speak of climate stability as a given, but Earth's history is a testament to its dramatic, often brutal fluctuations. Ice ages, supervolcanoes, and drastic temperature swings are not anomalies. They are intrinsic features of this planet's turbulent past and potential future. The unsettling truth emerges. Life on Earth exists not because of inherent planetary resilience, but within an astonishingly narrow window of conditions. Any slight deviation from this delicate equilibrium, and vast swaths of our seemingly vibrant world could quickly become uninhabitable, revealing a fragility often overlooked. Consider Earth's global temperature. A mere few degrees warmer, and the intricately balanced ecosystems we know would utterly collapse. Deserts would expand relentlessly, water sources would evaporate, and heat waves would render entire regions uninhabitable for complex life. Conversely, a drop of just a few degrees could plunge our world into a new ice age. Glaciers would creep forward, locking away vast amounts of water, altering coastlines dramatically, and suffocating life under an impenetrable blanket of ice and frigid air. This temperature sensitivity directly impacts the planet's vital water cycle. Subtle shifts mean more extreme droughts in some areas, while others face catastrophic floods. The rhythmic flow of precipitation, crucial for all terrestrial life, would become wildly erratic and unpredictable. Beyond temperature, our atmosphere, often taken for granted, is another finely tuned element. Imagine a minor dip in oxygen levels, even a fractional percentage. The implications for respiration, for fire, for the very metabolism of most complex life forms would be devastating and immediate. Or consider carbon dioxide. While essential for plants, too much or too little can throw the planet's entire greenhouse effect out of whack. A subtle increase could lead to runaway heating, making our current climate concerns seem trivial by comparison. The ozone layer, a thin shield in the upper atmosphere, protects us from lethal ultraviolet radiation. A minor weakening, even an imperceptible thinning beyond current levels, would unleash a torrent of deadly UV rays, sterilizing surfaces and ravaging life. Our planet's magnetic field acts as another crucial, yet invisible, protector against solar winds and cosmic radiation. A slight reduction in its strength could expose Earth's surface to a constant bombardment of energetic particles, causing widespread genetic damage and environmental decay. And what of the Sun itself? Our life-giving star, though seemingly stable, can fluctuate. A small increase in solar flare activity, or a minute but persistent surge in its overall output, would dramatically overheat our fragile world, making current heat waves unbearable. Descending beneath the waves, the oceans reveal another critical vulnerability. Even a slight increase in acidity, just a fraction of a pH point, begins to dissolve the very foundations of marine ecosystems: coral reefs, shellfish, and the plankton that form the base of the food web. Our journey into Earth's apparent perfection reveals a complex tapestry woven from countless fortunate events. It's not just one factor, but a delicate interlocking chain of circumstances, each narrowly avoiding disaster that allows life to persist. We begin with our place in the cosmic dance. The Earth orbits the Sun at a distance often called the Goldilocks zone, not too hot, not too cold. This precise solar proximity ensures liquid water can exist on the surface, a fundamental requirement for all known life. Veer slightly closer or further and everything changes. Yet it's not just the average distance. Our orbit is remarkably stable and nearly circular, minimizing extreme temperature fluctuations throughout the year. Many exoplanets endure highly elliptical paths, leading to immense seasonal variations that would challenge complex biology. Even the Sun, our life-giving star, is a lucky draw. It's a stable G-type star, not prone to the violent flares or short lifespans of many other stellar classes. A different star might have incinerated early life or faded before it could evolve. Beyond distance, consider our atmosphere. Its unique composition, primarily nitrogen and oxygen, is the direct result of billions of years of biological and geological processes. It's a breathable shield, not a toxic shroud like on Venus or a barren vacuum like Mars. This atmospheric blanket performs another crucial role, trapping just enough heat to maintain stable global temperatures through the greenhouse effect. Too little and Earth would freeze, too much, and it would boil away into a runaway greenhouse, a fate observed elsewhere. Then there's water itself. Not just its presence, but its sheer volume. Oceans cover over 70% of Earth's surface, acting as a global temperature regulator, a solvent for nutrients, and the medium in which early life could thrive and evolve. Water's anomalous properties, like expanding when it freezes, also play a part. This allows ice to float, insulating water bodies below and preventing entire oceans from freezing solid, a critical mechanism for aquatic ecosystems to survive harsh winters. Our planet's axial tilt, currently around 23.5 degrees, is another seemingly arbitrary parameter. This tilt is responsible for Earth seasons, distributing solar energy across the globe and preventing extreme temperature gradients that could make vast regions uninhabitable. Without this stable tilt, or with a wildly fluctuating one, entire continents could cycle between unbearable heat and deep freeze. Many planets experience dramatic shifts in their axis, leading to climatic chaos incompatible with long-term biological development. We often perceive Earth as a bastion of enduring stability, its vast oceans and towering mountains unwavering. Yet the conditions fostering life are not static, eternal truths. They are the fragile results of countless dynamic processes, constantly interacting, constantly balancing. This delicate equilibrium, precisely what makes our planet habitable, might be far more susceptible to rapid, catastrophic shifts than we are willing to admit. What if the foundational systems that regulate our global environment are not merely robust, but instead operate on knife edges? Imagine a complex machine humming along until a single critical component degrades, initiating a cascade. For Earth, this isn't just a theoretical concept. It's a historical pattern, albeit one we rarely witness in real time. The pace of change could accelerate, catching us unprepared. Our atmosphere, a seemingly endless expanse, is surprisingly delicate. Its precise chemical makeup, the balance of oxygen, nitrogen, and trace gases, is fundamental to life. A slight deviation, an accumulation of specific molecules beyond a critical threshold, can trigger dramatic and irreversible climate shifts. It's a thin, vital membrane, vulnerable to subtle yet potent alterations. Geological records tell a sobering story of past atmospheric transformations. Periods of intense volcanic activity, asteroid impacts, or even sustained biological processes have drastically altered Earth's air. These ancient changes, occurring over millennia, demonstrate the planet's capacity for dramatic atmospheric rearrangement, fundamentally reshaping the environment for every living thing. While past shifts often unfolded over vast timescales, current human-induced changes are happening at an unprecedented pace. The Industrial Revolution, a blink in geological time, has injected billions of tons of greenhouse gases, pushing atmospheric concentrations higher than seen in millions of years. This rapid alteration isn't allowing natural systems enough time to adapt or compensate. The danger isn't merely the initial change, but the self-reinforcing loops it can trigger. Warmer temperatures melt polar ice, reducing Earth's reflectivity, leading to even more warming. This isn't a linear progression. It's a spiraling descent where each step amplifies the next, pushing the system towards new, often hostile states. These feedback mechanisms are powerful, hidden drivers. Beneath the surface, our vast oceans, often seen as limitless, are also reaching critical junctures. They absorb enormous amounts of heat and carbon dioxide, acting as crucial climate regulators. But this capacity is finite. As they become warmer and more acidic, their ability to stabilize global temperatures and support marine life diminishes drastically, triggering vast ecological consequences. Ocean acidification, driven by increased CO2 absorption, is dissolving the very building blocks of marine ecosystems. Coral reefs, vital nurseries for countless species, are particularly vulnerable. As their intricate structures crumble, entire food webs are disrupted, threatening the biological productivity of the seas. This unseen chemical shift has profoundly visible repercussions. Deep ocean currents, massive conveyor belts of heat and nutrients, regulate global climate patterns. They distribute warmth from the tropics to the poles and draw cold water back. Disruptions to these currents, perhaps from massive freshwater influxes due to melting glaciers, could plunge regions into dramatic temperature extremes, changing weather systems worldwide. The oceans and atmosphere are inextricably linked. Changes in one inevitably affect the other, often with surprising speed. A shift in ocean temperature can alter atmospheric pressure systems, leading to more frequent and intense storms, droughts, or floods across continents. The calm blue surface belies the profound, dynamic power within, ready to reshape our world. Our very presence here, generations rooted in its soil, might be the strongest bias of all. We call Earth home, and that deep, primal connection shapes our perception, making it difficult to truly objectively evaluate its planetary merits. Is it truly the optimal world, or simply the one we adapted to? From a purely scientific standpoint, stripping away sentiment, what makes a planet objectively best for sustaining life, especially complex, enduring life? It's a question that forces us to look beyond our own blue marble, challenging assumptions ingrained deep within our worldview. Earth, undeniably, is good enough for us. It offered the conditions for life to not only emerge, but to flourish into the incredible diversity we see today. But good enough is a distinctly human assessment, reflecting our specific survival requirements, not necessarily an ultimate planetary ideal. Consider the sheer number of cataclysms Earth has weathered: asteroid impacts, supervolcano eruptions, ice ages, and atmospheric shifts. Life here adapted, evolved, and persisted, but often at great cost, pushing species to the brink of extinction repeatedly. This resilience is notable, but is it ideal? Imagine a world with a more stable climate, less geological upheaval, and a gentler evolutionary path. Perhaps one that doesn't regularly expose its biosphere to extinction-level events. Our familiar planet's history is a testament to survival, yet it's also a record of constant struggle. Take Earth's magnetic field, our shield against the solar wind. It's robust, vital, and without it, our atmosphere would have long since been stripped away. Yet its strength fluctuates and its poles notoriously flip, weakening protection temporarily. Could a more constant, stronger field exist elsewhere? Our dynamic tectonic plates recycle nutrients, drive volcanism, and contribute to atmospheric regulation. These are crucial processes. However, they also unleash devastating earthquakes and tsunamis, constant reminders of the planet's restless interior. Is there a less violent mechanism for geological renewal? Earth's axial tilt provides seasons, a driving force for biodiversity and climate. Yet this tilt also wobbles over millennia, altering global ice sheets and weather patterns dramatically. A world with a more stable, perhaps less extreme, axial tilt might experience greater long-term climatic predictability. Our planet's water cycle is incredibly efficient, supporting life across vast biomass. However, it's also responsible for devastating floods and droughts, often unpredictable and exacerbated by its own chaotic processes. Could a world have a more tempered, less volatile hydrological system? Earth's atmosphere, a delicate blend of nitrogen, oxygen, and trace gases, is perfect for us. But it's also a product of billions of years of biological activity and geological processes, easily perturbed. A slightly thicker, more resilient atmosphere, perhaps, could offer enhanced protection and stability. The very notion of a better planet challenges our deepest assumptions. For generations, Earth has been the benchmark, the only example of a world teeming with life. But this solitary perspective, while understandable, might also be our greatest blind spot in the cosmic search for truly ideal conditions. We've spent countless hours detailing Earth's vulnerabilities, its narrow habitable zone, and the ceaseless geological and atmospheric battles it fights. Now, the natural progression of our inquiry leads us to a profound, yet often unsettling, possibility. What if such struggles are not universal requirements for life? Imagine a world where stability isn't a fragile, temporary state, but an inherent planetary characteristic. A world where the fundamental forces of geology and climate conspire not for dramatic extremes, but for sustained, gentle equilibrium. This isn't science fiction, it's a cosmic probability. The sheer scale of the universe demands we consider alternatives. Billions of galaxies, each housing billions of stars, many with their own planetary systems. To assume that Earth, orbiting an average star in an unremarkable galaxy, represents the pinnacle of planetary potential would be an act of profound hubris. Astronomers now regularly discover exoplanets, worlds orbiting distant stars. Each new discovery expands our understanding of planetary diversity, revealing environments far stranger and, in some cases, potentially far more hospitable than our own blue marble. The data increasingly hints at richer possibilities. These distant worlds offer tantalizing clues. What if a planet could possess a stronger, more protective magnetic field, shielding life from stellar radiation far more effectively than Earth's? What if its atmospheric composition naturally filtered harmful rays, while retaining ideal temperatures without drastic shifts? The cosmic census suggests that rocky planets with inhabitable zones are not rare. With so many contenders, the statistical likelihood of some exhibiting superior traits, a Goldilocks zone optimized beyond Earth's specific balance, becomes not just possible but probable. We just haven't found them yet. Consider a world with a more stable axial tilt, eliminating extreme seasonal variations that drive so many of Earth's climatic challenges. Or a planet with a slightly larger core, generating geothermal energy consistently, perhaps sustaining subsurface oceans of liquid water for billions of years without fail. The concept of a super-Earth has emerged as a particularly compelling candidate. These planets, typically 1 to 10 times the mass of Earth, are often rocky but larger, potentially offering several advantages over our home world, challenging our terrestrial biases about optimal size. A super-Earth's increased gravity could mean a denser atmosphere, offering better protection from meteors and radiation. Its larger size might also allow for a hotter, more geologically active core, sustaining plate tectonics for longer, which is crucial for nutrient cycling and regulating climate. The sheer immensity of the cosmos compels us to consider this radical idea. Billions of galaxies, each home to billions of stars, suggest an astronomical number of planetary systems. To assume Earth's conditions are unique, or even optimal, across such a vast tapestry of possibilities seems increasingly presumptuous. The universe is a grand experiment. Our telescopes, though powerful, have only just begun to scratch the surface of this cosmic ocean. Yet with every new exoplanet discovery, the diversity of worlds astounds us. Some are gas giants, others scorched rocky bodies, but a significant fraction fall into categories that might, under different criteria, be considered truly advantageous for life. We often frame our search for habitable worlds around the Goldilocks zone, a region where liquid water could exist on a planet's surface. But this narrow definition might overlook entire classes of worlds, those with subterranean oceans or planets where different chemistries could thrive, making our ideal perhaps too Earth-centric. Consider long-term stability. Earth's geological processes, while vital, are also sources of catastrophic change. A world with a more consistent, less violent internal dynamic, yet still capable of nutrient cycling, might offer billions of years of undisturbed evolution, avoiding extinction events that reshaped our own biosphere. Then there's the atmosphere. Earth's protective blanket is crucial, but it's also a delicate balance, vulnerable to solar flares and cosmic rays. Imagine an atmosphere naturally thicker, or with a more stable composition, offering superior shielding without trapping excessive heat. Such a world could boast perennial, milder climates. Earth has experienced dramatic climate shifts, from snowball eras to scorching epochs. A planet with a more consistent axial tilt or orbiting a calmer star might maintain a remarkably stable temperature range across its entire surface, eliminating extreme seasons or volatile weather patterns, fostering constant, predictable conditions. Beyond atmospheric shielding, what about magnetic fields? Earth's magnetosphere deflects harmful solar wind, but its strength and shape fluctuate. A world with a consistently stronger, more stable global magnetic field could provide an unparalleled shield, allowing life to flourish without constant bombardment from radiation. Take super-Earths, for instance. These planets are larger than Earth but smaller than Neptune, often with greater mass. Their increased gravity might seem a drawback, but it could also mean a stronger, more stable core, retaining internal heat longer and sustaining a magnetic field for eons beyond Earth's lifespan. A larger core on a super-Earth could drive geological activity for much longer. This prolonged volcanism and plate tectonics are essential for cycling carbon, regulating climate, and replenishing nutrients. For life, this means a consistent planetary engine, minimizing the risk of a cold, dead core that plagues older worlds. Higher gravity could also mean super-Earths are better at retaining their atmospheres, preventing gases from escaping into space over billions of years. This allows for more enduring and stable atmospheric composition, offering a continuous shield against harmful radiation and preserving vital components for life. The profound implication of countless superior worlds existing elsewhere is unsettling. What if our beloved Earth, with all its breathtaking beauty and life, was never destined to be the zenith of habitability? What if, instead, it was merely an early, fortunate experiment in a cosmos capable of far grander designs? This thought shakes the very foundation of our understanding. For millennia, humanity has viewed Earth as the ultimate cradle of existence, a singular oasis in a barren void. Yet this perspective might be less about objective truth and more about a deep-seated, perhaps necessary attachment. We formed an identity around our home, projecting its characteristics onto the very definition of a perfect planet. This attachment, while fostering our initial survival and growth, may now be a blindfold. It prevents us from objectively evaluating Earth's intrinsic flaws or limitations when compared to the vast spectrum of cosmic possibilities. Is our affection for this blue marble clouding our scientific judgment about true planetary optimality? Our entire criteria for habitability are, almost by default, Earth-centric. We search for liquid water, temperate zones, and atmospheres similar to our own. But what if life, in its infinite ingenuity, thrives under conditions we currently deem hostile or even impossible, on worlds far exceeding Earth's subtle advantages? Imagine planets with thicker protective atmospheres that render magnetic fields less critical. Or worlds with stable, long-lived star systems that offer billions more years of consistent energy than our Sun. These are not just theoretical constructs. They represent plausible realities within the diverse cosmic tapestry we are only just beginning to unravel. Consider a super-Earth, perhaps one twice the mass of our world, yet possessing a core that retains internal heat for far longer, fueling geological activity and nutrient cycling over eons. Such a world might offer a stability and resilience that Earth, with its finite internal engine, can only dream of. Or ponder planets orbiting smaller, longer-lived M-dwarf stars, maintaining habitable conditions for trillions of years, vastly exceeding the Sun's expected lifespan. While tidal locking presents challenges, the sheer longevity offers evolutionary timescales that dwarf Earth's 4.5 billion-year journey, potentially allowing for life of unimaginable complexity. Such extended timescales could allow for the development of entirely novel biological strategies, perhaps even the evolution of species perfectly adapted to extreme environments we currently deem inhospitable. Our perspective, confined to Earth's relatively brief history, might be profoundly limited in grasping true potential. If planetary characteristics like geological stability, atmospheric protection, and stellar longevity are critical, then Earth, while good, might merely be average or even suboptimal when stacked against a universe brimming with alternatives. This isn't to diminish Earth, but to objectively assess its standing. Our very definition of perfection is inherently colored by our singular experience. We see liquid water and assume it's the only solvent for life, ignoring the potential for exotic biologies utilizing ammonia or methane under different thermal regimes. We project our own chemistry onto the cosmos. The question hangs in the cosmic void: if truly better worlds exist, where are they? Why, despite our ever-advancing technology and insatiable curiosity, have we not clearly identified these supposed planetary utopias? The answer, perhaps, lies not in their non-existence, but in the profound limitations of our current cosmic search. The first, most obvious hurdle is sheer distance. Our galaxy alone spans 100,000 light-years, dotted with hundreds of billions of stars. Each one a potential sun for unseen worlds. Even our most powerful telescopes can only resolve the faintest pinpricks of light from such astronomical reaches, let alone discern intricate planetary details. Imagine trying to spot a single grain of sand on a beach thousands of miles away. That's a crude analogy for the challenge of finding an Earth-sized planet orbiting a star light-years distant. The direct observation of such a world is an almost insurmountable task, a quest for a needle in a cosmic haystack. Most exoplanet discoveries rely on indirect methods, detecting the minute changes a planet imposes on its host star. A slight dip in brightness during a transit, a wobble in stellar motion caused by gravitational tug. These are not direct images, but subtle whispers of a world's presence, often barely perceptible. The signals we receive from these distant worlds are incredibly weak, often buried beneath cosmic noise. A tiny planet, ideally positioned for life, might only cause a minuscule flicker in starlight or an almost undetectable gravitational pull. These faint echoes are easily lost across parsecs of interstellar space. Our primary detection methods inherently favor certain types of planets. The transit method, which observes a planet passing in front of its star, is biased towards large planets orbiting very close to their stars. These are often hot Jupiters or super-Earths in extreme environments, not temperate distant worlds. For a transit to be observed, the planetary system must be perfectly aligned with our line of sight, an unlikely cosmic coincidence. If a planet's orbit is even slightly tilted, it will never cross its star's face from our perspective, rendering it invisible to our most successful detection technique. The radial velocity method, detecting stellar wobble, favors massive planets close to their stars because they exert the strongest gravitational tug. Smaller, potentially more habitable planets further out produce a signal too faint for current instruments to reliably discern amid stellar activity. Direct imaging, the dream of seeing exoplanets directly, is even harder. A planet is billions of times fainter than its host star, completely swamped by the star's glare. It's like trying to see a firefly next to a lighthouse from miles away. Only a handful of very large, hot, young planets have been directly photographed. This intense stellar glare is a fundamental observational blind spot. Any Earth-like planet residing in its star's habitable zone is perpetually overshadowed by the overwhelming brilliance of its sun. Special techniques are required to block this light, but they are still in their infancy. We define habitable worlds based on our single example, Earth. Our search parameters are often a mirror reflecting our own blue planet, focusing on liquid water, temperate zones, and an oxygen-rich atmosphere. But what if these very criteria blind us to other, potentially superior forms of planetary suitability? What if we've limited our cosmic imagination? Our current methods of exoplanet detection, like the transit method or radial velocity, are adept at finding large planets close to bright stars. This naturally biases our discoveries towards certain types of worlds, often gas giants or hot Jupiters, or rocky planets orbiting very close to their suns. Are we truly finding the most common worlds, or just the easiest ones to spot? Consider a super-Earth, a rocky planet several times Earth's mass. With greater gravity, it could retain a thicker atmosphere more effectively, perhaps even for billions of years longer than our own world. This enhanced atmospheric stability could provide a more consistent climate, protecting against solar flares and cosmic radiation over vast timescales. For planets orbiting red dwarf stars, tidal locking is common, creating a permanent day and night side. Traditionally, this was thought to be detrimental to life. However, recent models suggest that a thick enough atmosphere could distribute heat, creating a vast terminator zone with perennial twilight and stable temperatures, a perpetual garden. Red dwarf stars, though dimmer, are incredibly long-lived, burning for trillions of years, far longer than our sun's projected lifespan. A planet orbiting such a star, even if tidally locked, could offer an unprecedented duration of stability for life to evolve and thrive, free from the stellar evolution anxieties our own solar system faces. Our habitable zone concept is largely based on the presence of liquid water on the surface, requiring a specific temperature range. But life on Earth thrives in extreme environments, chemosynthesis in deep-sea vents, microbes and ice. Could similar, less conventional habitable zones exist, where different solvents or energy sources sustain abundant life? Worlds like Europa or Enceladus in our own solar system possess vast subsurface oceans, heated by tidal forces, shielded from radiation by icy shells. These worlds don't fit our conventional surface habitability criteria, yet they are prime candidates for harboring life. Are we overlooking entire classes of potentially teeming worlds? Earth's dynamic geology, with plate tectonics, volcanoes, and earthquakes, recycles nutrients crucial for life but also presents constant threats. Imagine a planet with a more stable, less volatile interior, perhaps larger, retaining internal heat longer for gentle geological activity, offering prolonged periods of uninterrupted calm for life's development. A robust and consistent planetary magnetic field is vital for deflecting harmful solar and cosmic radiation. A larger, more massive planet with a deeper, more enduring molten core could generate a far more stable and powerful magnetosphere than Earth's, providing a superior shield for billions of years, a true cosmic refuge. So while we meticulously scan the cosmos for echoes of home, could a multitude of truly superior worlds, more stable, more enduring, perhaps more suited for the long-term journey of life, lie hidden in plain sight simply because their definition of ideal doesn't quite match our own familiar blueprint? We naturally gravitate towards what we know, what feels comfortable. For millennia, Earth has been our sole reference point for life's ideal conditions. This ingrained bias makes it incredibly difficult to imagine a truly superior world that doesn't mirror our blue-green home. Our perception of perfect is inextricably linked to human experience, but the cosmos has no such limitations. What if the characteristics that make a planet supremely resilient and stable for billions of years are precisely those that would make a human uncomfortable? Imagine a world with an atmosphere dense enough to block nearly all harmful radiation, yet thick with gases unfamiliar to our lungs, perhaps even corrosive. A sky perpetually clouded yet nurturing. Consider a planet with higher gravity, a constant gentle pull that sculpts stronger life forms, but would leave us feeling perpetually heavy, our movements labored. This enhanced gravitational field might offer tectonic stability, protecting its core and maintaining a long-lived magnetic field far better than our own, preventing atmospheric stripping. Or a world bathed in light from a dimmer, longer-lived star, providing consistent, gentle energy for trillions of years. Its surface might appear eternally twilight to us, lacking the vibrant, direct sunlight we cherish. Yet this steady, mild illumination could prevent catastrophic solar flares and provide unparalleled evolutionary stability. The very definition of ideal must shift when considering cosmic scales. We seek comfort, life seeks persistence. A planet might maintain liquid water deep beneath its surface, protected by a vast ice shell, making it inhospitable for surface-dwelling humans, yet a bastion of enduring life shielded from stellar vagaries. Such worlds could possess an internal geothermal engine far more robust than Earth's, driving convection currents for eons without the violent, life-threatening plate tectonics we experience. This geological placidity could offer unparalleled environmental consistency, preventing mass extinctions caused by volcanic supereruptions. Perhaps the best world harbors an ocean not of water, but of cryosolvents or complex hydrocarbons, stable at incredibly low temperatures, supporting biochemistries we can barely conceive. These alien seas, while lethal to us, might offer a far more stable medium for the evolution of resilient, long-lasting organisms. Our concept of a habitable zone is tied to liquid water on the surface. But what if the ultimate Goldilocks conditions exist deep below the surface, insulated from cosmic radiation and temperature swings, in vast subsurface caverns or oceans warmed by tidal forces or radiogenic heat? A hidden, stable paradise. The colors of such a world might be entirely alien. Plants, if they exist, might reflect infrared light, appearing black or deep purple to our eyes or glow with bioluminescence. This spectral difference might signify a more efficient energy capture system, superior to our chlorophyll-based ecosystems. Imagine a planetary system with multiple large moons, providing immense tidal heating and geological activity, but distributed across several smaller bodies, rather than concentrating it on one. This might create a network of stable, tidally warmed worlds, each perhaps offering a niche more resilient than Earth's. Indeed, our ingrained perception of a good planet often revolves around immediate familiarity and comfort. We envision lush landscapes, breathable air, and temperate zones. But what if this narrow lens blinds us to a far more profound metric? What if the universe's truly optimal worlds prioritize longevity, not just momentary ease? Imagine a planet engineered by cosmic forces for billions of years of unwavering stability. A world where geological upheavals are rare whispers, not thunderous roars. Where atmospheric composition remains remarkably constant, shielded from drastic shifts by subtle, inherent mechanisms. This isn't a fantasy, it's a theoretical blueprint for ultimate planetary endurance. Earth, for all its beauty, has been a tumultuous experiment in life. Ice ages have carved continents, volcanic eruptions have reshaped our skies, and asteroid impacts have triggered mass extinctions. Our stability has often felt like a series of lucky breaks, a precarious balancing act constantly on the verge of tipping. Consider climate reliability. Earth's climate oscillates, sometimes violently, driven by orbital wobbles, solar flares, and even biological processes. A truly superior world might possess a built-in thermostat, a delicate yet robust feedback loop ensuring temperatures remain within a narrow, life-sustaining range for eons, undisturbed by external chaos. Then there's geological moderation. Earth's active plate tectonics, while vital for nutrient cycling and magnetism, also unleash earthquakes and volcanism. A more stable world might have gentler, predictable geological processes that recycle materials slowly, without the violent outbursts that repeatedly reset the evolutionary clock for its inhabitants. Atmospheric endurance is another critical factor. Our atmosphere has transformed dramatically over geological time, shaped by life itself, but also susceptible to runaway greenhouse effects or solar stripping. The optimal planet would possess an atmosphere so resilient, so perfectly balanced, that it could resist degradation for billions of years. Ultimately, environmental resilience defines a truly enduring world. It's the capacity to absorb shocks, adapt to subtle changes, and maintain life-supporting conditions without catastrophic collapse. Earth has resilience, but perhaps only within certain, surprisingly narrow, parameters that we are now actively testing. Such a planet might not boast the dramatic canyons or soaring mountain ranges that awe us on Earth. Its geological features might be subtle, its weather patterns monotonous in their consistency. But this seeming lack of dynamism could be its greatest strength, a testament to an underlying, enduring stability. Life evolving on such a world would experience an unprecedented continuity. Without the constant threat of global cataclysms, species could develop over far longer timescales, perhaps reaching levels of complexity and stability we can barely conceive. Evolution might proceed with less urgency, fostering deep, interconnected ecosystems. Earth, in cosmic terms, is still a relatively young planet. Its process is often characterized by a youthful, vigorous instability. Its dynamism has certainly driven incredible biodiversity, but at the cost of countless extinctions. Is a restless, ever-changing planet truly superior to a steadfast, unchanging one? The very qualities we often romanticize about Earth, its vibrant seasons, powerful storms, and dynamic geological forces, might actually be symptoms of a fundamental instability. We celebrate its constant change, yet perhaps a truly superior world would achieve harmony not through dramatic upheaval, but through enduring, gentle consistency. Could its very liveliness be its greatest flaw? Consider the sheer scale of Earth's environmental fluctuations. From scorching deserts to frozen poles, from towering mountain ranges born of collision to vast ocean depths, our planet is a world of extremes. This drama, while visually stunning, demands constant adaptation from every organism, every ecosystem, and every burgeoning civilization. Our familiar seasons, for instance, are a direct consequence of Earth's axial tilt. While they bring beauty and variety, they also usher in cycles of profound stress. The shift from lush growth to harsh winter, then back to spring, represents a continuous reset for vast swaths of the biosphere. In many regions, these seasonal transitions are not gentle. They are violent clashes of air masses, rapid temperature swings, and dramatic shifts in precipitation patterns. Entire populations of flora and fauna must migrate, hibernate, or perish, only to be replaced by new life cycles, a relentless churn. Such aggressive seasonal change might seem essential for biodiversity, but what if it's merely a mechanism for survival in a less than optimal environment? A world with more consistent, temperate conditions could potentially foster an even greater, more stable, and less stressed web of life. Then there are the extreme weather events that plague our planet. Hurricanes, typhoons, and cyclones born of warm ocean waters unleash destructive power that reshapes coastlines, devastates habitats, and claims countless lives. These aren't isolated incidents, they are an inherent part of Earth's atmospheric engine. Beyond tropical storms, blizzards bury entire regions under feet of snow, floods inundate lowlands, and heat waves bake continents, pushing ecosystems to their breaking point. These events are not exceptions. They are periodic reminders of Earth's volatile, energetic nature, a planet constantly at war with itself. A world where such widespread devastation is routine might be thrilling to observe, but is it truly advantageous for long-term survival? Each catastrophe requires immense energy for recovery, diverting resources from growth and stability to mere persistence in the face of relentless assault. The geological heartbeat of Earth also adds to its dramatic reputation. Tectonic plates, constantly grinding and shifting beneath our feet, give rise to majestic mountains and deep ocean trenches. But they also trigger earthquakes and tsunamis, shattering stability in an instant. Volcanoes, those awe-inspiring vents to the planet's molten core, erupt with unimaginable power, spewing ash and lava, reshaping landscapes and altering global climates. While they contribute vital elements to the soil, their activity is a testament to Earth's inner turmoil, a restless giant. The previous parts have explored Earth's hidden vulnerabilities, its dramatic history, and the precarious balance that sustains us. Yet, despite all the science, perhaps the most powerful illusion we cling to is not one of logic but of pure aesthetics. We believe Earth is the best, simply because it is undeniably beautiful. Our emotional attachment to this planet is deeply rooted in its visual splendor. Think of the vast, shimmering oceans stretching beyond the horizon, teeming with mysterious life. They represent bounty, tranquility, and the very origin of our existence, a blue marble in the dark expanse. We gaze upon their serene surfaces, yet forget the crushing pressures of their depths, the volatile currents, and the immense destructive power of tsunamis that reshape coastlines in an instant. Beauty can mask a formidable, indifferent force. Consider the lush, vibrant forests, a symphony of greens and browns home to countless species. They filter our air, provide shelter, and stand as ancient cathedrals of nature. These majestic woodlands symbolize life's enduring strength. But these same forests are fragile, susceptible to fire, drought, and disease. Their beauty is seasonal, their resilience tested by constant change. What seems eternal can vanish, leaving behind stark, barren landscapes, a reminder of their impermanence. Then there are the towering, majestic mountains reaching for the sky, their peaks often capped with snow. They embody strength, permanence, and ancient majesty, seemingly untouched by the fleeting concerns of life below, a testament to geological time. These very mountains, however, are the product of immense tectonic violence, slow-motion collisions that tear apart and reshape continents. They are not static monuments, but active, grinding features, occasionally erupting with volcanic fury or collapsing in landslides. And the sky above us, an ever-changing canvas of blues, grays, and fiery oranges. From the soft dawn to the dramatic twilight, it paints our world with breathtaking hues. The sky is a constant source of wonder, connecting us to the cosmos. Yet these beautiful clouds that drift lazily overhead are also the architects of storms, hurricanes, and blizzards. The atmosphere, so vital, is a thin, delicate film, easily disturbed, capable of both sustaining and devastating life. We are drawn to these dramatic displays: the crashing waves, the vibrant foliage, the soaring peaks, the turbulent skies. We interpret these vivid sensations, this dynamic interplay of elements, as signs of a perfectly balanced, ideal world. The illusion runs deep because our perspective is entirely internal. We are, quite literally, products of this planet. Every cell in our bodies, every synapse in our brains, evolved within Earth's specific atmospheric pressure, gravity, and chemical composition. How can we truly critique a home that built us from the ground up? We perceive normal as Earth's conditions. A comfortable temperature range, breathable air, liquid water — these aren't objective ideals, but rather the very parameters that allowed us to exist. Our entire sensory apparatus is tuned to this world, making it impossible to see it through truly alien eyes. Imagine a fish attempting to describe the ideal environment. It would undoubtedly champion water depths, currents, and specific salinity levels. It wouldn't conceive of a dry land as better. Its entire frame of reference is aquatic, just as ours is terrestrial. Our love for Earth is not just aesthetic, it's existential. We are emotionally tethered to its landscapes, its sunsets, its forests. These aren't just pretty pictures. They are the backdrops of our species' entire history, interwoven with our very survival and cultural identity. This emotional bond, while profoundly human, clouds our judgment. It makes us resistant to the idea that another world, perhaps starkly different, could offer superior conditions for life, even for our kind of life, given adaptation over millennia. We suffer from a profound survival bias. We judge Earth as ideal because we survived here. The countless species that perished due to Earth's less-than-ideal moments are silent witnesses, unable to offer their critiques of its volatile past. Every asteroid impact, every supervolcano eruption, every ice age tested life to its limits. The survivors adapted, becoming testament not to Earth's inherent perfection, but to life's incredible resilience despite its imperfections. Consider how our senses evolved. Our eyes perceive a narrow spectrum of light. Our ears hear a specific range of frequencies. Our bodies function within precise temperature and pressure boundaries. These are Earth-specific adaptations, not universal standards. If we had evolved on a world with a thicker atmosphere or weaker gravity, our biology would be fundamentally different. Our perception of comfortable or habitable would shift dramatically, making Earth feel alien and potentially hostile. This isn't to say Earth is bad, but to question its exclusivity as the best. We project our evolved needs onto the cosmos, searching for planets that mirror our own, unaware that we might be overlooking truly superior alternatives. This isn't just about our perspective, it's about our very biology. We are, quite literally, made of Earth. Our cells thrive in its specific gravity, its atmospheric pressure, its precise blend of elements. Every breath, every beat, every nerve impulse is calibrated to this world. What if this intricate, perfect fit is actually a profound biological blind spot, not a universal benchmark for ideal living? Life didn't choose Earth because it was objectively ideal. Life adapted to Earth's existing conditions, and in doing so, shaped itself to perceive its adopted home as perfect. From the deepest ocean trenches to the highest mountain peaks, terrestrial organisms have carved out niches, thriving in conditions that would annihilate biologies unfamiliar with this planet's specific quirks. Our very definition of habitable is skewed by our inherited limits. We seek planets with liquid water, a similar atmospheric composition, and a comfortable temperature range, simply because these are the parameters our earthbound biochemistry demands. It's a self-referential quest, limiting our imagination to environments that mirror our own cradle. Imagine a species evolving on a gas giant, perfectly adapted to immense pressures and exotic chemical clouds. Their ideal planet would be an atmosphere-rich world, a realm of constant, gentle currents, utterly devoid of a solid surface. Earth to them might appear as a terrifying, unstable, solid cage, completely unsuited for life. Our sensory organs, our entire physiological framework, are exquisite instruments tuned to Earth-specific frequencies. We see within its light spectrum, hear its atmospheric vibrations, and feel its gravitational pull. These are not universal standards of perception, but highly specialized tools, optimized solely for survival here. This deep biological fit creates a powerful illusion. We equate familiarity with superiority. Because our bodies function optimally within Earth's bounds, we naturally assume these bounds represent the pinnacle of planetary suitability. It's an understandable, yet potentially flawed, conclusion born from evolutionary success. Consider the subtle shifts in planetary conditions that Earth life has endured over billions of years. Each era saw dominant species rise and fall, not because the planet became bad, but because the environment shifted beyond their particular adaptive sweet spot. Only those with the right adaptations survived, proving adaptability, not inherent perfection, is key. What if an objectively superior planet for life offered more constant, less fluctuating conditions? A world with minimal axial tilt, resulting in virtually no seasons. Or a primary star with incredibly stable output, preventing the dramatic climate swings that have plagued Earth's history. Such consistency could foster far more efficient biospheres. Our biology, finely tuned as it is, requires constant internal regulation to cope with Earth's variations. Maintaining core temperature, blood salinity, and atmospheric pressure balance demands significant energy. A planet with inherently more stable parameters might allow life to thrive with less internal struggle, dedicating more energy to growth and complexity. Perhaps the best planet would be one that minimizes environmental stress, freeing organisms from the relentless evolutionary arms race against a changing home. Imagine a world where basic survival is less arduous, allowing for deeper specialization and the development of truly unique, less burdened biological forms. Our journey through the cosmos has revealed a profound truth. The concept of best is often a mirror reflecting ourselves. Earth, the cradle of our civilization, feels perfect because it shaped us, not necessarily because it possesses an objective superiority over the countless worlds awaiting discovery. This familiarity, this deep-seated emotional connection, can blind us to the extraordinary advantages offered by planets vastly different from our own. We've explored worlds with atmospheres that could shield life more effectively, or gravity that could foster stronger, more resilient organisms. Imagine oceans beneath miles of ice, harboring ecosystems utterly alien yet thriving with a vibrancy that challenges our narrow definition of life's potential. These are not barren wastelands, but complex environments, each a testament to nature's boundless creativity. Consider super-Earths, worlds with several times Earth's mass, often possessing denser atmospheres and potentially more stable geological activity. Their vastness might offer a grander canvas for life, or their stronger gravity a powerful evolutionary forge. These aren't just theoretical constructs. Telescopes are confirming their existence by the thousands. Each data point nudges us closer to understanding a universe brimming with planetary diversity, far beyond our initial limited scope. The very conditions we deem essential for life-temperate zones, liquid water on the surface, a certain atmospheric composition are predicated entirely on our own biological lineage. They are parameters, not universal laws. What if a planet with extreme geothermal vents, shielded from stellar radiation, proved a more stable environment for certain complex chemistries to emerge? Our definition of a habitable zone might be laughably restrictive. We cling to the image of a green and blue marble, believing it to be the ultimate benchmark. But the universe is not obligated to conform to our comfort or our limited frame of reference. It unfolds in myriad unexpected ways. The true best planet might be one where resources are so abundant they never pose a limiting factor. Or one with a magnetic field so robust it renders harmful radiation a non-issue, offering unparalleled stability for eons. Perhaps a world orbiting a red dwarf with its immensely long lifespan offers billions more years of evolutionary time than our Sun, allowing for forms of life and intelligence we can barely conceive.